Alright, so we start. So in the last class we had already discussed pre-training, and now we are going to discuss the fine tuning part of it. What is fine tuning, by the way? Sorry? So you know what is unsupervised training? This is what we had done for language modeling. Okay. What is the next thing? So what is supervised learning? So you have your input, you have your labels, corresponding labels. Okay. So this what was semi supervised? We saw in word2vec it was supervised task, but it was a dummy task, right? Word embeddings learned were a byproduct of doing something else. Now in case of fine tuning, what we are talking about is, so let me very quickly redraw this architecture that they have. So now we are going to draw. So this is text and position embeddings. Okay. Now, so double D here. Now, what was the next thing we will do? Masked multi-head attention. Then you do this thing, then feed forward neural network, layer. So then we had a layer norm again, and this one goes here. This whole thing is what? This is decoder block, and GPT-1 has 12 such layers, and once you are done with this, so what you could do is, what were the two tasks, what was the one task that we were doing? Next word prediction, right? This is what we were doing, this is what we had discussed until now. Okay, now, so maybe I can add a plus here, but this is same as add. Okay. So now, so this particular network was trained for giving the probability of next token. Now they said they want to do it for other NLP tasks too. So let's say the task that they are talking about is, so I'll take examples from the Stanford lecture here. So you have tasks something like this, various NLP tasks. Okay. One simple thing, so if you look at the figure 1 of the paper, one simple thing that you can do is classification. What is classification? What is classification in this context? So maybe sentiment classification, you are given a piece of text, you are also given the corresponding labels, right? Let's say 3 classes we are talking about, positive, negative and neutral. So output, which class does this given text belongs to? Now, how would you otherwise do it? How would you otherwise do it if you don't have this one? Right, but I mean, what will be the training procedure? So you have this annotated data set. For every example, you train your whatever network, LSTMs or whatever, okay? And the weights that are learnt, they are very specific to this particular task, right? Because this is the problem you are solving. What about this architecture? You are learning a completely different thing. You are learning just to predict the next word. Now they claim in this paper is, can we use this network that we have just trained to do other NLP tasks too, right? So can we use this? So this is now, you have trained this to do this. So this they call pre-trained. Now fine tuning means I am not going to learn all these things from scratch when I am going to do NLP tasks. So for example, if I am trying to do, let's say, sentiment classification, so when I am going to do sentiment classification, let's say in positive, negative or neutral classes, right? How would you otherwise do? You have these labels, you have examples and you are training your network on this. But what we are supposed to do here, so what authors have here is, they say we do these two kinds of things. Next word prediction is their pre-training, but you can also do classification. So what are you supposed to do in this case now? You will input, so let's go ahead with this. Now, how can we do sentiment classification using this network? How can we do sentiment classification using this network? So let's say, so let me do something of this kind. I have, so these are my labels. So these are basically my Y's labels. Now X is my input. I can say it is like, you know, sequence of x1, x2 all the way until xn, let's say. So even if I have used n somewhere else, you know this is a different n, okay. So this is your input, sentence, document, whatever, this is your label. How do I classify for these labels using this network? So let us say this is class 1, 0, minus 1. So if let's say minus 1, 0, I mean it does not matter. You could have simply taken 0, 1, 2 as well. Does not really matter at all. Yes. How can you solve this using this problem? I mean this network. So what is the output size here for GPT-1? Here this, how many outputs are here? How many outputs are here? How many input do you give? t equal to 512. 512 inputs of size 768 cross 1. So how many outputs will be there? 512 outputs, each of size 768. Now, which of these vectors, which of these outputs is the richest one? Richest in the sense that it has seen all the things. Yes, maximum that this network has gone through. The last one? Why not the first one? Because first one, this was masked for everything in the right, whereas if you talk about this last vector, right, it has taken attention, so it has attended to all the words before it. So remember that one vector that we were talking about in LSTMs, that this one vector is supposed to encode the whole sentence, the whole encoder, right? This vector is something like that. It is encoding this whole input that this network has seen. So what you do, what is the dimension of this guy? 768 cross 1. So how do I classify? How do I classify? This is easy. If you can't do this, right. So basically what you are supposed to do is, how should my network up there now look like? So this is 768. You have 3 classes here. This is a fully connected, so fully connected layer. Everybody is connected to everyone. And all you are supposed to do is softmax over here. That's it. This makes sense? Okay. So let's talk about some other task now. So let's say this time the task is, so let me talk about entailment. And NLP researchers, they have created a lot of data sets. So you remember, there is one data set for NER, there is one data set for sentiment classification, one for entailment, question answering, summarization, and similarity calculation, and so on, right? So now they start working on these data sets. So entailment is this problem. Example I am taking from Stanford slides. So entailment is this problem. You have a premise. Premise is the man is in the doorway. And your hypothesis is the person is near the door. Okay. So you have 3 classes. Label pair of sentences as whether they are, so whether it is an entailment, whether it's contradictory, or whether it is neutral. So again 3 classes. Right? Is this problem clear? You will have 2 sentences, two parts of text. One is called premise, another one is called hypothesis. We have seen these kind of things in some competitive exams. So man is in the doorway, the person is near the door. There is an entailment here, right? So, for this particular example, class is this. How do we solve this problem using the network that we have pre-trained? So, what they say is this problem clear first of all? Okay. So, what they say now is, so of course, right, one thing that I forgot to mention here was, this input that you are giving now, this input that you are giving x1 to xn, it is marked by an end of sentence and a start of sentence. So, these two things are different from what you had seen before. There is a start of sentence, there is a end of the text. Okay. And do I need anything else in classification thing? Probably not, because this whole monolithic statement, that document, that statement, that review is given to me. It starts at a place, it ends at a place. So, that is it. I need only these two new tokens. What else? In this case, what do we do? So, in this case, what do we do? So, what they say is you do something like this. Start, this is the token S, and then premise, and then a delimiter, then you have this hypothesis, then you have, let me call it AND. What are you going to do with this? What is this? Right. So, this is my input. Input to whom? The transformer GPT-1. Okay. So, this is what you input to transformer. Can I call it GPT-1? So, let us say GPT-1. And what do I do next? What do I do next? What should come here? A linear layer, and then of course you will take a softmax on that. So, you have linear plus softmax. This is what you have. So, everybody understands the structure here. We will discuss all these things, I mean, but so input, this means this whole thing you are feeding at the starting point. So, of course, you are giving the embeddings plus positional embeddings, add them and feed it. So, and then this whole thing passes through my 12 layers transformer GPT-1, and then finally, so now talk about that last element. So, which one are you talking about here? This particular, what are the dimensions of this vector that you are feeding into this linear layer? 768 cross 1. So how will my last layer look like? Because until here it is just GPT. Last layer will look like exactly same as I had drawn here. Because it is 768 cross. So you have 3 classes. This is exactly the same. This is how it will look like. Okay. Now, so this was our second problem. Now let us go to third problem. Third problem that they talk about is similarity. Your data set is, you have text 1, you have text 2, and you are just supposed to tell me whether they are similar or not. Okay. So how do we do this now? So this is just binary classification. Either you will say yes or you will say no. Okay. So now again, how do I draw this? Start and then text 1, then comes delimiter, yes, then you have this text 2, what will come last? Extract, or I am calling it and then this whole thing you feed to GPT-1. What do you do in the last? Linear plus softmax. Make sense? But here they do something more. They don't just do this. Okay? Here they do something more. So I'll maybe get rid of this. So here they do something more. What they say is, start text 2, delimiter text 1 and GPT-1 Why so? Why this one? What are you trying to capture by having text 1 here and then text 2 and then reversing the order and then finally whatever comes out? So what will be the size of this guy? 768 cross 1. This will also be 768 cross 1. You add them. Whatever comes, feed that to this binary classifier. So why do you think they might be doing this? See, they say in the paper that it does not really matter whether you are computing the similarity of text 1 with text 2 or text 2 with text 1. The ordering does not matter here. So that's why they want to capture this thing, that whether text 1 comes before or text 2 comes before it does not really matter. Okay? Question answering. Now, if you are given a multiple choice question, how will you fit it into this kind of a thing? So what they say here is, So the problem here is of this kind. You are given some context, so you are given some comprehension, you are given a question, and you are given some k multiple choice answers. You have to select one. So if you have to select one out of k, what should I do in the last? So softmax over k classes. That is done? Okay. Now what will be my input? My input to this linear plus softmax will be what? That is always going to be 768 cross 1. Now how do we make, like, how do we prepare this whole thing that we have been doing? So start, then comprehension. So what they say here, they do it this manner. So they concatenate the document context and question with each possible answer. Okay. So this is what they do. Context. This context is basically concatenation of your the comprehension and the question, right? So this is basically your comprehension plus question. What do you do next? Now you can guess. There has to be a delimiter. What is this delimiter, by the way? What does it mean? What is the purpose? Right. So it separates the two pieces of text. That this, so this is not a continuation of text 2. It's a separate one, right? Up there. Similarly, this is not a continuation of text 1, and so on. So what should come here? What should come here? Delimiter? Now what next? Comprehension plus question is already there. What is remaining? Answer. Question is already there. So now answer 1. This is my first option. Okay, that's a good one. So instead of, let's say, option 1. No. Awesome. Bilkul. So this is AND, right? This goes through my GPT network, and then finally what will be the output? The last one, right? So in all these examples you are always taking the last token, that they are calling extract token, because it is extracting the whole information from this network. So now this guy is 768 cross 1, but this was for option 1. How many options do you have? 4 or k in general. Okay. So you have k such things. What will you add? What will you do with them? Take all of them, add, and give it to whom? Linear plus softmax. How many classes? So softmax is over k classes, because you have to give me one of these answers. Okay. So they end up showing that this method of training was much better than, training for individual example. So if you have a question answering data set, you train LSTM for this particular task, that state of the art results were inferior to what they have done. Does this make sense? Because this is what you will be doing now. So once I am done with BERT, next topic will be BERT, then we will be doing programs. So in that you will write, almost one line for everything, but in order to be able to understand what is that function doing, we need to understand all this theory. Okay. So you have this. Now if you are supposed to so can you train GPT-1, for example? If I ask you to train GPT-1 from scratch, can you train? Maybe you have all the expertise to do it, but not the hardware. Okay? And we would be still lucky if we were to train just GPT-1. GPT-2 is 1.5 billion. GPT-3 is 175. Okay? So this is increasingly insane. Now, so you can't really do this. What you can do is take a pre-trained network. Last fine tuning we can do. This is a very small thing. 768 vector comes to me, and who gives this to me? So there is a library, there is a model out there. I give input to it. Model passes, so this input passes through this whole pre-trained thing, gives me a 768 vector. I train this small network here, which is 3 cross 768, that I can do on my laptop itself without any problem. Okay, and then do whichever of these tasks you were doing. Okay, so this is called fine tuning. Now what are the options you have in this? So you want to make it more fully connected layers? Fine, you can do that, but generally I have not seen that, because see, you have already passed through 12 layers of GPT, so that 768 vector is very rich. You won't need that. I mean, you can do that, but so what options do you have? In this case, we said we are not going to touch the parameters of GPT-1, right? We just feed it the input. Okay. So what are the extra things we are supposed to do? You are supposed to learn word embeddings for this start, end, and delimiters, because these are the things you have introduced which are not there in original GPT-1. Okay. Other parameters are the last layer, that linear plus softmax that you have introduced. So you are supposed to learn just these parameters. But anybody stops you from learning the whole GPT-1? No. What you could do is, so what we did just now is called fine tuning, but what I am going to tell you now is also called fine tuning. So if you start solving this problem, any of these, and you decide to train GPT network as well, will it be called fine tuning or what was it? Pre-training. Why fine tuning? Right. So if you don't start from random initialization of weights, what you are doing is fine tuning. So you are starting from where GPT ended. So those weights are already very good ones. So you don't want to start from scratch. But what you are saying is, I still want to tune those weights a little bit based on my specific problem itself. Now you can also decide to train, for example, this GPT-1 was a stack of 12 layers, 12 decoders. You can also decide कि I will not change the first 6, I will train only the uppermost 6, okay, and so on. You can do all kind of combinations that you want to do, depending on how much compute do you have. Okay, so this is the fine tuning, and they of course show better results on 9 NLP tasks of 12 that they touch. So on 9 tasks, their results were better than the state of the art specific network for these individual problems. So what they say is GPT learns the language and then you give me a data set. I need to do very little tweak to this GPT architecture and I am still doing better than what I was doing before on that specific network. So if your application is always going to be a sentiment classification task, you by default have it inside. I mean, see, here you see it outside, but in the end, there is no inside outside. There is just one layer after the other, right? But for drawing purpose, we are drawing it this way because this is not the part of original GPT. This is something, so this is an extra idea they are having. Ki we have trained a language model that works awesome. Now we also want to see whether other NLP tasks, whether this network can be used to solve those problems too. And it turns out very much, and in fact much better, because you trained just one big network, not 12 different big networks. And they outperform your individual networks specialized to do that particular task. Questions here now? I think I am done with what I had to say. So now I am talking about section 3.2, which is supervised fine tuning. Now, what was the cost function for our language modeling? Log probability of UI, I mean, okay, I am just following the papers thing. So this is what it is. We are just computing the probability of my ith token given previous k tokens, and we are doing it for all the things in the corpus. So my corpus is basically so my C is basically from U1 sorry, there is no C in this case, there is U. So my U is basically from U1 to, I am again using N, okay. Now this was the loss on which language modeling was done, okay. Now how will the loss for these guys look like? What are we doing in these pre-training things? We are computing the probability of this is given by softmax. So we are not doing anything special here, we have done all this. So what are the dimensions of Wy for my question answering problem? What is Wy for my question answering problem? K cross 768, right? What is HLM? This is my last token, right? This is my last token that is capturing the whole document, and we were taking softmax over that, so there is nothing new. So you are saying that the probability of Y, where Y is the label and this is my input. So now L2C is summation over all examples log P this should make sense to you. It does. All we are saying is this is the same probability you are computing. So, since this is also a classification problem, you are simply taking the categorical cross entropy. This is what it is. And I hope this goes up last time. And then they also mention this thing that I have not seen in any other lectures, but GPT-2 and GPT-3 seem to be heavily using it. So, what they said that we also train L3. So, I will just write it down and then we go. L3C is some L2C plus lambda L1C. Okay. So, this is what they finally, this is, nobody has asked me what is C. Sorry? L1 was this one. L1 was your loss for the main objective of GPT, which was language modeling. This was for your classification. And now they are saying if you, instead of first training it over this and then over this, if you train it over this, then it also yields good results. They do it for lambda equal to 0.5. So, half comes from here and 1 comes from here. Okay. So, I think that is it for GPT-1. C, okay, C is my corpus. So, C is your labeled corpus. I think that is it for today. Sure. Questions here? GPT-1 is over. So, this complete paper is over. You can now go and read. In particular, their final results, if you want to see the graphs and everything, that will be helpful. कितने लोग हैकाथन में जा रहे हो ये बताओ मेरे को.